This section, we're going to talk about symmetry. Okay, so if you would like to pause this and just read over the objectives, go for it. What we're going to do is we're just going to determine the graph is symmetric with respect to x-axis, the y-axis, and the origin. Determine whether the function is even, odd, or neither even nor odd. All right. The next thing of the objectives, we're going to consider the points. So we're giving an order pair here, 4, 2, and 4, -2 as an example. And that appear on the graph of x equals y squared. It's going to be on the next slide. We'll get to that. So the points like these have the same x value. If you notice, both x values were 4, but the y values were opposite signs, right? 2 and -2. These values are reflections of each other across the x-axis. And I'm fixing to show you what that means. If for any point x, y on the graph, the point of y or x, -y is also on the graph, then the graph is said to be symmetric with respect to x. Or you can hear the word about. So let's look at it. This is what it's saying. That I have this function, hang on a second, get my pencil rocking. We have this function of x is equal to y squared, right? So we know we got a parabola because of the squaring. And since it's set equal to x, we know it's going to open to the right or to the left. And since y has a +1 on it, we're going to say it opens to the right. If it was negative, we'd open to the left. But anyways, since it's a positive, we opened to the right. And the origin here is going to be the center of the or what we call the vertex. I called it the center of the parabola, but it's the actual vertex of the parabola, the belly of the parabola. And if you notice, my x is 4 right here, and it's 4 right here. So this parabola is in respect to the x-axis. So it's symmetric about the x-axis. Okay, so now let's go to our next one. Our next slide said, well, let's consider the order pair 3, 4 and -3, 4. So now what do we have? We have our y values that are the same right here. But our x values are the opposite. And we're given this function where y equals x squared minus 5. And let's go to that next slide and look at it. Now, points like this have the same y value. So let's look at it right before I go to the next slide. X squared tells me it's a parabola. Since it's a positive x right here, +1 on the x, we know it's going to open upwards because it's set equal to y. If it was a negative x squared, we would have opened it downward, okay? Let me erase this so the rest of the stuff will pop back up, maybe. There it goes. Okay, so again, points like this have the same y value, but opposite x values. So that means we're in reflections of the, across the x-axis. It's going to be across the y-axis. Okay, it says the x. We're going to cross the x's if it's, let me just go down here right quick. Instead of reading it, let me just come down here. So we have these order pairs, right, of -3, 4. So we are crossing the x-axis at this point and on each side of the parabola. And then the belly sits on the y. If this would have opened downward, we wouldn't have crossed the x-axis, right? So this is symmetric about the y-axis. Okay. Now it says, let's consider the points of -3 square root of 7. So if we consider those points there, we're going to we can go graph it, right? And if we go graph it, let's make sure my screen didn't jump too much. Let's look for a second. That was at 8 of 7. Okay, we're good. Okay, so they said if we took these two order pairs, you notice that the x's are the same but opposite signs. The y's are the same but opposite signs. So now we have the x squared is equal to the y squared, and we're going to graph this on the next slide. If for any point x, y on the graph, and the point negative x, negative y is also on the graph, then the graph is said to be symmetric with respect to the origin, which makes sense. So we got this going on. We got this x squared equals y squared plus this 2. This is, sometimes we get ellipses, and this one here is a hyperbola. So whenever we plot these points, you notice that we got this and it's respect to the origin, because there's happening on both sides of the origin. So algebraic tests of symmetry, the x-axis, if replacing y with negative y produces an equivalent equation, then the graph is symmetric with respect to the x-axis. If on the y-axis, if you're replacing the x with a negative x and it produces an equivalent equation. So what it's saying equivalent, if you notice that when we were looking at these, they were showing on both sides, look, they're equivalent. Even though this is the negative value for x, this is the positive value for x, excuse me. So we got this in respect to y axis. This one here, my x has the same x value here, and they're both the same positive, but my y's are opposite signs, right? So it was respect to x. So that's all this is, just telling you how to recognize that. And the origin, if the replacing x with negative x and y with negative y produces an equivalent equation, then the graph is symmetric with respect to the origin, and that's what we got here. Okay, so example 1 said, let's solve this. We got x squared plus 2 for the symmetry with respect to x, which makes sense. It's set equal to y, right? And the x has the squaring on it. So we do have a parabola going on. So if we solve this, we can say, oh, okay, let's look for its negative value. So that's what they did here. And we're going to distribute that negative sign, and that's where we get this one. So we got our original, and then we applied the negative to this. The resulting equation is not equivalent to the original. Would you agree that this here is not equal to this other one? Okay, so we are going to say, because we're trying to determine, right, if it's respect to x, y, or the origin. So since it's not equivalent to the original equation, so the graph is not symmetric with respect to the x-axis, okay? Now, you would check to see if it's in respect to the y-axis. And so what we're going to do, let me erase this here. Let's see if it's in respect to the y-axis. So if these two would have been equal, we would have said, oh, it's in respect to the x-axis. So, and now let's take our original again. And let's put the negative just on the x squared. So when I square that negative sign, I get a positive x squared plus 2. So now when I do this, the resulting equation is equivalent to the original equation. So the graph is symmetric with respect to y. So now let's backtrack just a second, and maybe this will help, because I feel like by this point here, you're going to be, I'm confused. All right. Whenever we had respect to the x-axis, we had the same x value, right? Same, they're not opposite signs or anything, but we had a positive 3 and a negative 3. We had same numbers, but opposite signs for the y value. Then that would give me respect to x if by plugging in that negative value for y in the original, and then of course we got to distribute it since it was on the outside, because you can't have a negative, can't say y equals, you can't say negative y equals. You could say, So we have to distribute, and that's where we get this. So then we can compare those two, right? We can compare those two to each other. Are they equal? And in this case here, no, so it's not in respect to X. However, if yeah, it's not respect for X. However, if I said, let's take and plug that negative and apply it to just the X value, not the Y value, just the X, and we didn't have nowhere to distribute it because it wouldn't set equal to X, and it gave me my original, then it is respect to X, the Y axis. Okay, I hope this makes sense. My apology. I kind of get a little tongue-tied sometimes. So again, I applied the negative value here to determine if once I cleaned it up, if the original is equal to applying the negative to the Y value, gives me the original, then it is respect to X. If not, it's not. And then I took and applied the negative value to the X. And if it gives me the original is equal to the change, then it is in respect to the Y value. In this case here, it's respect to Y value. Okay. Let's move on. Oh, there you go. And there's some more information on it. And here's the solving of just plugging in the X, the negative for the X. All right. Now let's talk about our next example. And this is just showing you what it looks like on a graphing calculator. If y'all need to, you can use Desmos. It's got a free online graphing calculator. So this one here says, let's replace X with negative value, and let's replace the Y with the negative value. And if the changed equation is equal to the original, then we're going to say it's in respect to the origin because we replaced X and Y, right? So here we go. We put the negative on the Y and the negative on the X. So when we put the negative on the Y, we have to distribute it. However, before I distributed it, I thought, oh, this negative X needs to be squared, and that became a positive, right? Then you distribute it, it gives me negative. This original is not equal to this, so it is not in respect to the Y, or the origin, Okay, so one more time. If I put the negative on the Y, I'm looking for respect to X, right? If I put the negative on the X, then I'm looking for respect to the Y axis, the Y. If I apply it to both X and Y, then we're looking for the origin. Okay. Hopefully that helps. Sometimes reading all this can get a little confusing. All right, so let's move on. Now, we want to determine if it's even and odd functions. If the graph of the function of f is symmetric with respect to the y-axis, we say that it is an even function. That is, for each x in the domain of f of x is equal to f negative x. If the origin of a function of f is symmetric with respect to the origin, we say that it is an odd function. That is, for each x in the domain of f negative x is equal to negative f of x. Okay. So, and when we look at this, when we're talking about the origin again, you remember it's saying both x and y are negative. Okay. So that's what we got here, which makes sense. And let me get my highlighter going. So if you notice, they plugged it just on the X and nowhere else. So now we are talking about the Y. If you notice, they plugged it on the X and then they plugged it on the Y. Because remember, f of x equals y. Then we got to the origin. Okay, and we can say it's odd if it's to the origin, and we can say it's even to the Y. It's what they're saying here as an example. So let's move on. So we're going to determine if it's even and odd. So this one here has f of x, semicolon. We're going to find when we apply the negative sign to the x, and then then f is even. Okay. If I place the negative on f of x and simplify and compare it to this, then, and they are equal, then the f is odd. Okay, so you may want to print this out, write it in a little bit more, in a more format that's easier to understand for you. I totally understand. Sometimes it can get just a little bit confusing, but once you get it, it's going to be good. So, except for the function f of x is equal to 0, okay? A function cannot be both even and odd because 0 is not negative, it's not positive, right? So if it's equal to 0, then we cannot have both even and odd. Does that make sense? So if I have a f of x is not equal to 0, and we see in step 1, so if we go back up there, that f of x is equal to f negative x, that is f is even, we cannot continue, okay? So let's look at this one here. This example says, determine whether the function is even, odd, or neither. Okay, so you're giving f of x is equal to 5x minus 6x cubed. That 3 goes on there, minus 2x. So what we're going to do is we're going to apply the negative to the x. So we're going to put it everywhere as we see it, right? So we got this negative sign going on. And what happens? So negative raised to the 7th power. It's an odd power. So it's just going to be negative, and then we're going to bring it out to the front. So I got negative 5x to the 7th. I got this negative raised to an odd power. It's still negative. I need to bring it out to the front. Negative times negative is positive. And then this is, again, we're going to bring it out because it's an odd power because, 1 is odd. So negative times negative. So this is how we get this answer right here. Okay. So, and then let's finish this one up. It said, so see that we have f of x. So what we want to do is compare it to the original. And since this is not equal to the original, we're going to say it's not even. Okay. And that's what this statement here is saying that we took our original, set it equal to when we made the change on x. And since it's not equal, that's what that line through the equal sign means. It's not equal. Now let's determine if the function is even, odd, or neither. So what we're going to do is we're going to plug the negative to the f function, right? We're going to plug it to the outside of it. Let's plug in the rest of this right quick. Okay, so we plugged it in on this outside, and we're going to distribute to everywhere's inside. So I got negative times positive, that's negative. Negative times positive, or excuse me, negative times negative is positive. And then I had another negative times negative is positive. So my answer is this. So what is it saying? It's saying that this here, after we applied it, is actually even, right? Oops. Let's just clean this up. It's actually even to the change that we made when we said, oh, f minus x, right? Remember that gave us this. Oh, positive, because we had negatives coming out of those odd roots or odd powers. So this is equal to this. And since it is, we're going to call it an odd function. Okay. This next slide is showing you what this function looks like on the graph when you plot it. And you'll be able to see the origin and it's symmetric about the origin. You can see that. And then it is an odd function.